These notes are a review of the nature, origin, and relevance of various mass wasting processes, and the different ways in which erosion acts to modify Earth's surface. Mass wasting isn't the sexiest label for these processes, but if you've ever seen a rock fall in person, you know it can be very exciting indeed. Mass wasting events, like the rock slide shown here, can be a thundering cascade of excitement, for a few seconds at least. We care about mass wasting because processes such as landslides, mud flows, and rockfall are natural hazards that commonly impact humanity and can threaten life and property. California has 4 seasons: earthquake, fire, mudslides, and drought, is a common saying that reflects on the fact that seasonal mudslides and related events are a part of life. For instance, the intense rain that fell in 2018 in Southern California caused debris flows that killed 21 people. Epic mud flows are not restricted to California. In 1985, volcanic-related mud flows, called Lahars, buried the Colombian town of Armero, killing at least 20,000 people. And in 2015, a landslide-induced mud flow toppled buildings and killed 73 people in Shenzhen, China. Landslides, both large and small, can be deadly, like the one that killed up to 2,500 people in 1963 at the Vaillant Dam in France. We obviously need to pay attention to these processes and understand them, so we can better predict and hopefully avoid such catastrophes. Mass wasting is constantly going on all around us, and coupled with stream erosion, helps shape much of the Earth's surface. Typically unseen mass wasting processes, like rockfall, debris flow, landslide, etc., work in tandem with the more obvious erosion by the Colorado River to form the modern Grand Canyon. Simply put, mass wasting is the downslope movement of material under the influence of gravity. The many ways in which this occurs are classified based on a few important characteristics. First is the type of movement, whether it's falling, flowing, or sliding. Then there's the type of material that is moving, including rock, soil, sediment, snow, ice, etc. Finally, the rate of movement can range from instantaneous to imperceptible. Bedrock is not the only material that moves, and there are a few terms worth noting. One is regolith, which refers to soil, sediment, and small rock fragments that cover bedrock. The word debris refers to mass movement material that is coarse-grained and has larger fragments, whereas earth refers to material that is more fine-grained. Here are 2 helpful classification diagrams. The one on the left shows the type of material, style of movement, and rate of movement. The one on the right is similar and shows more examples. Now let's review some of the different types of mass wasting processes. We start with fall, the extremely rapid free fall of rock, regolith, or ice from a cliff. Rockfall is my personal favorite type of mass wasting, largely because of the excitement factor on hearing or seeing rocks fall and tumble down slope, making thumping and clattering noises as they go. Yosemite National Park is a great place to go for rockfall enthusiasts. Earthfall commonly occurs along steep, silty riverbanks. Where glaciers flow into lakes or the ocean, icefall is part of the glacier calving process. Freefall of rock is the process of rockfall. Contributing factors include the freeze-thaw cycle, where water expands as it freezes. This is also called frost wedging. Rockfall also occurs in locations where steep cliffs are undercut by stream erosion, wave erosion, etc. Also, in areas prone to seismic activity, earthquakes often initiate rockfall. A rock may bounce or roll after free fall in an area called a rockfall shadow. rockfall poses an ever-present hazard in these areas beneath steep cliffs. If the amount of material is great enough, a rockfall may transition into a larger rock avalanche, like the one shown here that occurred in Yosemite National Park in 2017. Talus is the sloping mass of rockfall debris deposited at the base of a cliff, like here below the cliffs of Mount Rushmore. Fine-grained talus is called scree, like this scree slope here near Tilico Peak in the Himalaya. Both talus slopes and scree slopes can be quite steep. Talus typically forms cone-shaped debris piles, like these exposed along the cliffs of Isfjorden on the Arctic island of Svalbard. As previously noted, Yosemite National Park sees significant rockfall activity. This figure shows the volume and timing of various rockfall events recorded between 1857 and 2011. Rockfall can occur at any time during the year, but the larger volume events tend to occur during the winter months. The 2014 Wapama Falls rockfall involved 16,000 tons of material, whereas the 2017 El Capitan event was almost twice as big. In Yosemite National Park, the rugged glacially eroded granitic terrain offers prime locations for rockfall due to the combination of the exfoliation of the highly jointed granitic bedrock, abundant precipitation, freeze-thaw weathering, and of course, the sheer cliffs. The massive cliffs of Yosemite Valley include iconic monoliths like El Capitan. Its geology is well displayed on its 3,000-foot cliff face and includes late Cretaceous intrusive rocks like the El Capitan granite, the Taft granite, diorite, and various other intrusive units. Rockfall has likely been occurring since the retreat of the glaciers about 15,000 to 18,000 years ago. Historical records indicate more than 1,000 rockfall events in the park in the last 150 years, with maybe 60 to 70 per year of varying sizes. At least 24 people have been killed in rockfall events since 1857 and more than 100 injured. For example, a rockfall occurred on September 27, 2017 on the southeast face of El Capitan in the area of the Waterfall Route, which is one of the many climbing routes on El Capitan. 30 climbers were on the wall when, without warning, a huge slab broke loose and generated an 860-ton rockfall, killing one climber below. The next day, a much larger 28,000-ton rockfall occurred from a point just above the previous day's event and propagated upward from there. It's estimated that this event was the 29th largest rockfall in Yosemite National Park on record. Then there's iconic Half Dome at the east end of Yosemite Valley. Half Dome is composed of the late Cretaceous Half Dome granodiorite, which rises nearly 5,000 feet above Mirror Lake and the floor of Tenaya Canyon. So, rockfall is common in this area. For instance, an event in June 2020 occurred along the Porcelain Wall, involving 3,100 tons of rock. In July 2015, after a heavy rainfall, a 100 by 200 foot sheet of granite, 3 to 10 feet thick, delaminated from the northwestern face of Half Dome, generating a 2,500-ton rockfall. And the Awaya Point rockfall on March 28, 2009, was the largest in Yosemite National Park since 1987. Approximately 115,000 tons of rock fell and tumbled over 2,000 feet, burying part of the Mirror Lake Loop Trail. This event generated ground shaking equivalent to a magnitude 2.4 earthquake. Of course, rockfall occurs in other areas of the park. Northwest of Yosemite Valley, just east of Wapama Falls on the Hetch Hetchy Reservoir. A large rockfall occurred on March 31st, 2014. Here, roughly 16,000 tons of Cretaceous granitic rock fell around 500 feet. No one was hurt, but about 400 feet of the Rancheria Falls Trail was destroyed. Here are some rockfall locations from Grand Canyon and Zion National Parks. Talus from a rockfall that originated in the Coconino Sandstone provided fresh exposures and new fossil finds, which were being explored by Dr. David Elliott and his graduate student, both from Northern Arizona University. There's Dr. Elliott. You can barely see him amongst the jumble of Coconino boulders. A relatively fresh rockfall occurred in the spring of 1970 at Colorado River Mile 7.1, and this one began in the Kaibab Formation and tumbled downslope to the river. The vertical cliffs at Redwall Cavern produced a tiny rockfall that impacted our boat motor. That was a close one. And in 2015, a large rockfall forced the closure of State Highway 9 in Zion National Park. Debris fall, or earthfall, involve free fall of regolith from a cliff. These are common along steep stream embankments, like here along the Minnesota River and here along the Colorado River. Earthfall typically involves fine-grained material and or soil and often transition into more of a slump or an earth flow. Topple is the slow to rapid forward rotation of a mass of rock, regolith, or ice, essentially like a domino falling over. While topple involves the same factors that contribute to rockfall, fracturing, jointing of rock, and ice greatly increase its occurrence. Strong, highly jointed, cliff-forming rock units, like this sandstone in Canyonlands, are prime candidates for topple. Topple is also common along stream embankments and along the edge of calving glaciers. Slides are the slow to rapid downslope movement of material along a distinctive surface, typically a fracture or bedding plane. There are two basic types of slides, depending on the shape of the slide surface. Translational slides occur on planar surfaces, like the one that occurred here near Gaviota, California, whereas rotational slides occur along curved surfaces, like here near Pomona, California. All slides are typically referred to as landslides. Translational slides occur on planar surfaces of weakness, typically where the ground surface is parallel to the weakness plane. Examples include bedding within sedimentary rock units, foliation within metamorphic rock units, rocks with significant joint fracturing, and faults. These slides result in simple movement of material downslope and involve minimal rotation or tilting. Block slides are a type of translational slide where the rock mass moves along the slide plane as a coherent unit. You can see that happened here in Deep Springs Valley, California. Rock slides are similar, except that the rock mass breaks into fragments as it slides. See example here from Gunnison County, Colorado. Debris and earth slides can also occur above planar slip surfaces. Translational slides are hazards that need to be considered in the construction of roads and buildings. The 2016 rock slide on Colorado Highway 133 is a great example. Larger slide masses typically disintegrate into many smaller units. What may start as a block slide may transition into a rock slide, then a rock avalanche, or even a debris flow. This transition is aided with higher water contents and higher movement velocities. Contributing factors to translational slides are the orientation of layers or fractures, the steepness of the slope, and the degree of water saturation in the slide rocks and along the slide plane. where the layering or fractures are parallel to the ground surface, are prime situations for translational slides. The steeper the dip of the layering and the slope, the greater the shear force and chance of slippage along the weakness plane. An added factor is that increasing water saturation significantly decreases the friction along the slip plane. Snowmelt, rain, and earthquake activity were the cause of the massive 1925 Gros Ventre landslide in Wyoming. Note the orientation of the rock layering with respect to the ground surface. The Gros Ventre landslide is located just to the east of Jackson Hole and Grand Teton National Park in Wyoming. On June 23, 1925, roughly 38 million cubic meters of mostly sedimentary rock slid down the north slope of Sheep Mountain, crossed the Gros Ventre River, and climbed 300 feet up the opposite valley slopes. Heavy rains and snowmelt saturated the Ten Sleep sandstone and underlying Amsden Formation shale. These weakened sedimentary layers, oriented parallel to the mountain slope, were also undermined by the erosive action of the Gros Ventre River at the base of the slope. The landslide created a dam over 200 feet high, which blocked the flow of the Gros Ventre River and created Lower Slide Lake. This was just the latest slide to block the Gros Ventre River. Several other large landslides are located upstream, including the Slate Creek, Upper Gros Ventre, Dry Cottonwood Creek, Goosewing Creek, Soda Lake, and Bacon Ridge slides. Rotational slides involve the slow to rapid sliding along a curved surface of weakness that is typically oriented concave up. Movement along this curved surface usually results in rotation or tilting of the slide material. This process is typically referred to as slump. This landslide in the Mud Creek area destroyed part of the Pacific Coast Highway in 2017. Rotational slides typically develop in weak but uniform material. A scarp, or small cliff, commonly marks the top of the main breakaway surface, and several slump blocks may form between the head and toe of the slide. The 1993 Holbeck Hall landslide in England is a prime example of a rotational slide, or slump. The main factors contributing to rotational slides include steep water-saturated slopes, intense rainfall, or earthquake activity. Depending on the degree of water saturation, the slide mass may transition into a debris flow, earth flow, or even a mud flow. La Conchita is a landslide-prone area on the California coast, where several major landslide events occurred in 1995 and 2005. Rotational slides are common along the margins of large mesas and plateaus, especially ones that have relatively weak units. This is the case along the margins of the Vermilion Cliffs in northern Arizona near Lee's Ferry. Failure of weak Chinle Formation mudstones lead to numerous slumps and rotational slides. This scenario is also seen along the margins of Black Mesa, located north of Black Canyon City in central Arizona. Here, slide activity is largely due to failure of relatively weak Chalk Canyon Formation sediment and volcanic tuff beneath the more competent cliff-forming, mesa-capping basalts of the Hickey Formation. Located in north-central Arizona, the Vermilion Cliffs form the southern edge of the Paria Plateau and represent the second step of the Grand Staircase, and also form the southern boundary of the Vermilion Cliffs National Monument. And since 1996, the cliffs have been home to a growing number of California condors. Originally 6, now there are 116 as of 2022. The Vermilion Cliffs are composed of Triassic and Jurassic sedimentary rocks, with alluvial and Aeolian sediment covering much of the floor of House Rock Valley to the south. The Chinle Formation is mostly covered by surficial sediment and is exposed at the base of the cliffs in this area. Next comes the sandstones and mudstones of the Glen Canyon group, exposed along the edge of the plateau. These include the Jurassic Moenavi and Kayenta formations, and the cliffs are capped by the massive Aeolian Navajo sandstone. This kind of lithologic sequence typically results in instability and slide activity along the margins of mesas and plateaus. This is because weaker units, like shale, evaporite, volcanic tuff, etc., are prone to failure when overlain by more competent strata, like sandstone and basalt. This instability can be further enhanced by groundwater activity and water saturation of the weak basal units. The Owl Rock and petrified forest members of the Chinle Formation form the main weakness layers here. As we continue farther south and east along the plateau margin, we come to the section dominated by landslide deposits. In this area, the distinctive grayish petrified forest member of the Chinle is exposed at the surface. You can see multiple slide blocks where coherent sections of strata have rotated and slid down intact. That's the Chinle through Navajo section exposed in this block. These rotated slide blocks are also called Torreva blocks. At least 3 separate mass wasting sequences are displayed in this particular area. The most recent slump blocks are adjacent to the parent escarpment, whereas older, more eroded slide blocks are located over a kilometer south of the main escarpment. And even younger rock avalanche deposits overlie these slide blocks and the intact grayish petrified forest member of the Chinle. Other types of mass-wasting surficial deposits cover the petrified forest member in this area, from rock avalanche to earth flow deposits. Here's another beautiful example of a rotational slide block. And just to the east in the Sandhill Spring area, we can see several active springs located at the boundary between the Chinle Formation and overlying Moenavi Formation. These springs represent the groundwater processes that helped initiate the landslide activity in this area. 4 distinct slide block sequences are visible here, with the oldest located farthest from the Vermilion Cliffs. The rotational slides of the western Vermilion Cliffs were first described over a century ago. The multiple sequences of landslides present along the plateau margin suggest a sustained history of cliff retreat due to various mass wasting processes. These slides most likely occurred during periods of the Pleistocene Ice Age, where the climate was much wetter. The Agua Fria National Monument, north of Phoenix, is a landscape of basalt-capped mesas cut by the Agua Fria River and its tributaries. Perry Mesa to the east and Black Mesa to the west are capped by the resistant basaltic flows of the Hickey Formation, which is Middle Miocene in age, 15 to 10 million years old. To the south, these flows overlie a sequence of interbedded basaltic flows, fluvial to lacustrine sediments, or stream and lake sediments, and volcanic tuffs of the Chalk Canyon Formation. They're a little older, early Miocene in age. This is a conducive situation for mass wasting. As the Agua Fria River is cut down through the sequence, the weaker Chalk Canyon Formation units have failed, producing areas of rotational slides. Here are 4 landslide areas in the lower Agua Fria Canyon. This area below Black Mesa is an eroded and faulted basalt-dominated landslide complex. A crude stratigraphy is locally exposed within the slide mass that includes thin sediment layers interbedded with basalt flows. Slide-related faults likely form many of the linear drainages. Similar basalt-dominated slide masses are present east of the river, with older slides overlain by younger ones. Slide deposits, colluvium and talus, cover much of the underlying Chalk Canyon Formation. Here, intact Chalk Canyon Formation is partially buried by a landslide mass. As we move farther north, the Chalk Canyon Formation thins and eventually pinches out against the more massive and resistant Paleoproterozoic bedrock. Thus, the potential for landslide development here is minimal. The infamous initial lateral blast of the 1980 eruption of Mount St. Helens was triggered by a landslide collapse of the upper part of the stratovolcano. Earthslides involve the slump of regolith, which is the combination of soil and soft sediment. Flow involves very slow to very rapid downslope movement of material as a viscous fluid. These range from creep to debris flow to rock and ice avalanche. Water content is typically variable. 2 different examples of flow are shown here. In 2015, this small rock and ice avalanche was caught in the act on Mount Cook in New Zealand. And this debris flow in the Snake River Canyon of Wyoming covered 300 feet of highway in 2011. Rock avalanches are the very rapid downslope movement of dry bedrock fragments. These are typically generated by a rock slide or even a rockfall and are commonly triggered by earthquake activity, volcanic eruptions, or heavy rainfall. In 2016, this large rock avalanche was deposited on top of the Lamplugh Glacier in Alaska. A spectacular rock slide avalanche occurred in 2013 in the Bingham Canyon Mine in Utah. Incredibly, no injuries occurred during this event due to ground monitoring studies by Kennecott Copper. Debris avalanches are the very rapid downslope movement of water-rich regolith and debris that are commonly unchannelized. Factors that contribute to debris avalanche events are areas with steep mountain slopes and water-saturated regolith. They are commonly triggered by earthquakes, volcanic eruptions, or large landslides. 30,000 people perished in Yungay, Peru during the May 1970 Nevados-Huascaran debris avalanche and mudflow. The event was triggered by the 7.9 magnitude Ancash earthquake, which destabilized the glacier and snowmass on the notoriously unstable north peak of Huascaran, located in the Cordillera Blanca, and is the highest point in Peru, at 22,205 feet. The twin peaks of glacier-capped Nevado Huascaran form the highest point in the Cordillera Blanca of the Peruvian Andes. On May 31, 1970, the 7.9 magnitude Ancash earthquake triggered a massive rock and debris avalanche, debris flow, and mud flow that destroyed the Peruvian town of Yungay and nearby settlements. The western face of Huascaran Norte is notoriously unstable and is prone to generating debris avalanche events. Both Yungay and Renrahirca were devastated in 1962 and 1970. Nevado Huascaran is not only the highest point in Peru, but the highest in all of Earth's tropics, and fourth highest in the Western Hemisphere. And as the name implies, the high peaks of the Cordillera Blanca are blanketed by glacial ice. Seismic ground shaking during the May 1970 event dislodged a huge 2,600-foot wide slab of rock off the west face, which then fell about 2,000 feet before impacting on the glacier below, initiating a massive avalanche of rock, ice, and snow. The avalanche achieved incredibly high velocities as a result of acceleration down the low-friction glacial surface and the cushion of air trapped at the base of the flow. The avalanche advanced rapidly downslope to Yungay at estimated speeds of 175 to 220 miles per hour, picking up more material on the way. After traveling over 8 miles from the origin of the avalanche in less than 2 minutes, the hurricane-like mud flow and debris flow buried the Yungay area in an estimated 80 million cubic meters of mud, rock, and debris. It's hard to say exactly how many people perished in this event, possibly as many as 22,000 or more, likely making it the deadliest avalanche disaster in history. In the Philippines, the village of Quinsagon was destroyed by a February 2006 debris avalanche. This event involved a large translational landslide and debris avalanche induced by a 10-day period of heavy rain. About 1,100 people died as a result. Snow avalanches are similar to the other avalanche types, but involve snow and ice. Point release avalanches are more localized than the broader slab avalanches. If you have ever skied in the Rocky Mountains or other mountainous areas, you are no doubt familiar with the potential dangers of these events. Debris flows are the slow to rapid downslope movement of a water-rich slurry of mud, soil, and rock, regolith essentially. More than 50% of the fragments in debris flows are sand-sized or larger. Flow is typically channelized, meaning they follow the stream channels, with debris fans at the lower end. Contributing factors include steep gullies and water-saturated regolith. Debris flows are commonly triggered by intense rainfall, rapid snowmelt, and even other landslides. Here are several examples of debris flow events. Intense rain triggered a 2014 debris flow that covered U.S. Highway 50 in Poncha Canyon, Colorado. This debris flow in Rocky Mountain National Park displays the typical channelized flow transitioning to a debris fan. In 2018, these homes were buried by a debris flow in Montecito, California. And large boulders tumble along in a 2016 debris flow in Switzerland. In December 1999, intense rainfall triggered 1.8 million cubic meters of debris flows, which flowed through Caraballeda, Venezuela, and killed as many as 30,000 people. Many buildings were washed out to sea during this event. The coastal areas of north-central Venezuela are infamous for mass wasting events like mud flows and debris flows. Deeply weathered, foliated metamorphic rock rugged terrain, and high rainfall have produced alluvial fan deltas at major coastal drainage outlets. These deltas are areas of high population density, like the cities of Caraballeda and Maisha near the capital Caracas. Numerous large historical debris flow events have occurred since the 17th century. For example, 10 days of torrential rain in December 1999 caused flash floods and debris flows that killed thousands of people along the coast in the Vargas region. During this event, torrential rainfall caused thousands of small landslides, stripping the soil and rock off the steep slopes of the Sierra de Avila, forming debris flows that traveled down narrow stream valleys to the sea at estimated velocities of 5 to 35 miles per hour. The large fan of the San Julian River at Caraballeda was one of the most heavily damaged in the December 1999 event. The resulting devastation was enormous, especially on this and other highly urbanized fans. Here's an incredible view of a debris flow moving through Caraballeda. The USGS estimated debris flow mud flow deposition on the Caraballeda fan was around 2 million cubic meters. Debris flow deposits ranged up to 5 meters thick, with boulders as much as 5 meters in length. An exact number of deaths resulting from this tragedy is difficult to determine, as there was no reliable census data for this area, and only about 1,000 bodies were recovered. Many people were buried or swept out to sea. Earth flows are the slow, downslope movement of water-saturated earth, mud, and soil, typically on gentle to moderate slopes. These typically acquire a characteristic hourglass shape, like this one in southern Australia and this one at Mission Pass, California. This earth flow occurred in the Northwest Territories of Canada. Note the hourglass shape. Mud flows are the very rapid movement of water-rich, fine-grained regolith that contains more than 50% sand, silt, and clay. These are more fluid than debris flows. They are basically like wet earth flows. This image shows the fluid nature of a mud flow, while this one shows the end result of a mud flow event. How does the saying go? Lahars are essentially volcanic mudflows. They originate on volcanoes as melted snow and ice combines with volcanic ash. Lahar deposits typically contrast with snow and ice capped volcanic slopes. And here, a 1991 lahar flows down the Pasig Potrero River on the east side of Mount Pinatubo in the Philippines. This 1989 lahar is seen flowing down a river valley near the Santa Maria volcano in Guatemala. Creep is the extremely slow downslope movement of rock and soil. This process can result in deformed rock layers, bent tree trunks, tilted fences, soil ripples, etc. Here's a typical example of the effects of soil creep on a moderately steep wooded slope. Solifluction is a type of creep common in Arctic regions. This occurs as the frozen soil layer, or permafrost, thaws and produces an active, water-saturated layer. Arcuate solifluction lobes are distinctive signatures of this process. Complex landslides are relatively large landslide events that typically include a combination of two or more mass movement types. One example of this is the La Valette complex slump mudslide mudflow in the French Alps. Another is the Musqua complex slide earthflow in British Columbia. Well, that's all for now. Till next time.